All right, so let's finish up this chapter on forecasting. So actually, I brought again my Farmer's Almanac, courtesy of Lowe's, right? I bought it. They weren't giving them away. But one of the things, if you're kind of familiar with what they do, it's kind of a neat little book. But yeah, they give like kind of long-term outlooks. And that kind of reminds me of climatology forecasting. So with climatology forecasting, you basically say, oh, this time of year, this general location, you're kind of expecting this weather. Okay, so you don't need a computer. You don't need any initial conditions. You're just thinking, this is kind of what it is. Okay, actually, here in a minute we're gonna say, well, how good is your forecast? And basically, there's something called forecast skill. And if this is about your skill level, then you don't have much skill. So you're like, hey, you're not going out on a limb, right? With climatology forecasting. Persistence forecasting, again, do not need a computer, do not need initial conditions. What persistence forecasting says is, the weather you have is the weather that you're going to keep. It's just going to persist. Go on and on and on. Now here, that doesn't work in Iowa very good, especially if you kind of get those Rossby waves going. You kind of have an alternating patterns of weather. Okay, some places it works pretty good.
We've never made up our minds.
So, yep. The next one is the analog approach. Now, to me, you do probably need a computer for this one. Because if you're familiar with the term analogous, analogous means you are finding something very similar. Okay, so what you do is you look in the past in your records for an analogous day. And so maybe this time of year, maybe 3 years ago, the weather was just like this. Okay, so then whatever happened the next day 3 years ago will be our forecast for tomorrow. Okay, it's an analogous approach. These next two kind of go together, trend forecasting and now forecasting. Again, this is something that you may already kind of apply on a regular basis. Especially like if I think of our snow systems that come through, you know, if you see Denver's getting hammered, you're like, oh, well, the next few days we could see some of that white stuff too. That is trend forecasting. Why? Because Denver is to our west, and systems here in the Ferrell cell actually come from the west. So that's kind of how that goes. Trend forecasting. Nowcasting is a little bit kind of closer to the right now time. So I guess nowcasting might be like if you look in Des Moines, okay, and you're like, you can kind of see the way the steering winds at upper elevations kind of been bringing stuff across. You're like, yeah, they've got it now. I think we'll have it in a few hours. Okay, so that would be like more nowcasting. So I have a few slides to kind of remind you how we've been talking about the butterfly effect. If a butterfly flaps its wings in South America, it has consequences globally speaking because it disturbs the air. That's kind of weird. But at upper elevations definitely is a player to what our weather is going to be or not be. And so I've got some more of these isobaric maps. I think we talked about an isobaric map before. An isobaric map basically gives elevations, and it's another contour line one, so you kind of see lines. But these are what we call iso heights that you need to get to in order to get that pressure. So here, sea level, I don't know if you remember millibars, we're talking about 1,013 millibars or so in general. Okay, so an 815 millibar pressure, you need to go up about that high. Okay, a 700 millibar pressure, about that high. Okay, because you have less air over you. Okay, 500 millibar, okay, 300 millibar, 200 millibar. So these isobaric maps are basically giving you kind of a snapshot at different elevations. So when we look at these isobaric charts, you might see some kind of waviness in their contour lines. Granted, their contour lines are iso heights, but they kind of go well with isobars. And then the wind flowing between the isobars. So we said that if wind is flowing straight, we call that zonal flow. If it's got waves, kind of gives us our troughs and our ridges, we call that meridional flow. So this is an 800 millibar isobaric map. So of the isobaric maps we're going to look at, or I mentioned, 800 millibars is just a little bit above Okay, we're about 1,013, so 800 millibars. These would be ISO heights to get 800 millibars worth of pressure. So you can kind of see the waviness. Looks like a trough there, pair of ridges. Okay. Remember that lows are associated with troughs, highs are associated with ridges. Okay, so that was 850 millibars. This is a 500 millibar isobaric map. We would expect as we go up in elevation, we expect the wind to be getting faster. Okay. Then at 200 millibar isobaric map, that means you should have 200 millibars of pressure above that. So these are ISO heights. We kind of see that pink color is actually showing you the jet stream. So this all kind of works together to kind of anticipate what our forecast, what we can expect. So with regard to anticipating severe weather, especially, what the polar jet stream is doing or not doing can be a player when it comes to, TS here stands for thunderstorms, just like these are Midwest thunderstorms. If the jet stream is running kind of strong, actually that can give us twists that we need for those mesocyclone, the wind shear, to get those mesocyclones going within those cumulonimbus clouds. So strong jet stream can maybe bring more, our tornado season can be worse. But strong jet stream messes up those hurricanes. So, and kind of vice versa. If the jet stream's kind of wimpy, I always think of, when I think of jet streams, I think of people that are taking hot air balloons trying to go around the world. They need the jet stream, but if it's kind of petering out, actually then that's good things for fewer tornadoes, but maybe more hurricanes. So long-range forecasts are put out, because they can't be put out by Norman, Oklahoma, because there are storm watch people, right? But these would be looking at kind of almost climatological data sort of stuff. So they're put out by the National Center for Environmental Prediction, or actually the Climatological Prediction Center under NCEP. So in order to kind of look long-term, one of the things that these folks are looking at are the sea surface temperatures. And remember, we talked about sea surface temperatures and we talked about El Nino and La Nina. So long-range forecasts are kind of the 3-month. I've got an example looking at coming up to show you. Long-range forecasts. Are they accurate? Yeah, I don't think they're definitely not meant to pinpoint storms or anything like that. But they can be a good, if you're a farmer or something like that, kind of give you a sense for what's coming up. And so these forecasts would use models. They would use different models than kind of our hourly or short-term forecast. Okay. So these are an example of the kind of the 3-month, November through January of a particular year. They don't go out on any real limb there, but they're based in science, okay, with models and kind of understanding what's going on at the time. So another topic, or kind of winding down, one last topic is why forecasts go wrong. And there are 3 reasons, and they're all on this slide. So one is that, remember, your computer requires you to give it a program. You get to pick the program, okay, or the model. And those programs or models are kind of like, it's hard to entirely know what Mother Nature's going to do. So the models aren't 100% correct. The second reason why forecasts are inaccurate, okay, is that we talked about using the ensemble method of forecasting to kind of say, combat the fact that if your thermometer says 32, actually that could be anywhere from 30, 31, 32, 33, or 34. You're like, 30 to 34. That's what your thermometer says. And what ensemble forecasting does is maybe, in that example, make like 5 different forecasts with the slightly different temperatures, and you get different results. That's ensemble forecasting. So that whole kind of uncertainty in the initial conditions, you're like, I don't know. You just got to put something in and see what your computer's going to spit back. But, There's uncertainty associated with all of those initial conditions. And the other one, and I'll go grab the globe over here again. The other one is, the computer can only give us a forecast as good as the program, that's number one, and as good as the initial conditions we feed it. So the problem comes in when it say holes. Basically, we've got all sorts of data here. People sending up weather balloons, you're having a good time doing that. We have your ASOSs, we have all sorts of initial conditions. But you get out to here where there's no people. Heck, if you just get out to, maybe some parts of here where there's no people, right? Those are holes. And so there are different ways to kind of smooth the data and kind of fill in those holes, but those are definitely holes. Okay, so those 3 reasons why forecasts it's hard to get it right.
Are there buoys in some of those oceans like there are off Florida and stuff too?
I think so. I don't know how much in the middle of the ocean you'd see buoys, but definitely kind of along the coast, I think I've seen maps where they are. So, if you're going to be wrong all the time and keep your job, well, how does that work? So that's why, forecasters are like, they got to keep their job because the deck is stacked against them. So let's talk about how a forecast could be wrong. Well, actually, one of the things the second bullet says is, like, if you look at a 10-day forecast now, you're like, really, how sure are you in 10 days that that's what it's going to be? But if you look at, like, tomorrow's forecast, you're like, oh, you might be right. So intuitively, the farther out, you're like, may not be right. So your error increases as you go out. But this is the one I told you about, the climatological approach. Basically, if the best you can do is say, this time of year, we kind of run somewhere between, it's cold right now, but somewhere between 40 and 70. If that's the forecast you're going to put forth, that doesn't take any skill. Okay, so forecast skill basically says, get out of the whole mode of climatological approach, and can you really kind of say what tomorrow's going to be? So with regard to saying how good a forecast is, we have the sort of forecast that doesn't have numbers. So, for instance, the whole cloudy, not cloudy thing, did they get that right? That would be a forecast quality. Then there are the things that actually do have numbers, and we can kind of do some statistics there. Say for the next 5 days, say the high is going to be 58, 62, 70, 49, that sort of thing. We can actually go back after it occurs and see how correct they were. Okay, so we can actually come up with an accuracy measurement against what they forecasted. So let's just say that a forecaster would definitely catch themselves if they see that they're always predicting high temperatures or temperatures that never come to be. Okay, if it's bias high or bias low, for instance with temperatures, they might want to say, I better choose a different model. Or whatever my model says, I better knock it down 2 degrees. I don't know. Okay, so forecast bias is something you do not want. So I think I mentioned that there's a website out there, and I put this on the Twitter feed. There's a website that actually says how good these different weather organizations are at putting out weather. Picture like 30 years ago. I'm not thinking there was the whole internet thing. I have to think 30 years ago.
It's not around here.
Okay, yeah, it wasn't as prevalent. So 30 years ago, basically you got your weather forecast from your nightly news. Your meteorologist there. But since then, now these days when I ask students, what's your favorite place to go out, I get AccuWeather, Weather Underground, kind of this semester I picked on, and there's Intellicast. There's just also the Weather Channel, okay? They all kind of, from what I can tell, have kind of the same access to initial conditions, but they might use different models, okay, and give us slightly different forecasts. So this is actually going to C2632. This is supposed to be neutral, as far as I know. Notice that it gives us our 5-day weather forecast. But what I want to draw your attention to is this stuff down here. And I know it's for Burlington because they didn't have enough data for Keokuk. But they're ranked kind of for descending order of accuracy. So the most accurate one last month was Weather Underground, 81%. Notice the National Weather Service pulling kind of down 76%, right? And there's a tab up there to click, well, how did they come up with that percentage? And they kind of talk you through it. But last year, kind of a similar thing. Notice the weather bug doesn't even make it to, I don't think, our top list for right now. In the past it has been. Oh, but look at the other thing. This is how accurate they were a year ago. This is how accurate they are now. Isn't that cool? So you little whippersnappers don't know how good you got it. Okay. Persistence, I'll have to click on that. I don't know if that's its own, but we talk about persistence forecasting. 42%. I mean, I don't know if it's like an organization or that sort of thing. But I thought that was neat. Okay. So like I said, and intuitively you guys would tell me the closer to now that your forecast is for, the more likely it is to be right. Heck, we could even use persistence forecasting for the next 10 minutes, right? Because the weather's going to persist in what it is. So we've definitely gotten better with regard to short-term forecasting. Very short-range forecasting. Short-range forecasting is a little bit farther out there, 12 hours to a few days. And notice that actually the whole 12 hours to a few days comes into account when you're trying to kind of focus on what's going on with regard to our hurricanes or tropical cyclones. Okay, back in '85, this is kind of the cone they were looking at, the error at these 12 hours to several days. And now, they cut it by a third, that cone of uncertainty. That's pretty cool.
Actually, that was like 9 years ago, so it might be better now.
Yeah, that's true. 2006, they probably gotten even better than 111 miles. So then we bump it up a few days to a couple of weeks. And this is where it kind of emphasizes what needs to be improved is actually the intensity. Okay, we've seen that before. They tell us that we're going to get a snowstorm kind of far out like that, and then nothing comes of it. Or they say that it's not going to bring much precipitation, and then it hits us hard. Okay, so, and then 4 weeks and beyond. It's somewhat useful. Again, as you kind of get farther out there, it's got less certainty with it. And then we kind of end with those 3-month sort of forecasts. That's all I have today. So this chapter will be due when you come take your test on Friday. Okay? All right. Don't forget to cover your plants tonight. Get down through it.
I know. I can't cover my petunias that are already planted. They're just